So hello, everybody. Thanks for staying till the end. And thanks for the organizers for inviting me. Before starting, I want to make a disclaimer. In this talk, I will tell you a lot of things about background and not too much about what I have done. And the reason is that I don't know how many people are familiar with this topic. And I thought it was more important actually to, sort of explain what is this topic, why it is important, what are the basic techniques, and then maybe a little bit later, just a little bit of what we have done that it might be too technical, but still. Okay, so what is this about? This is new lower bound for stochastic non-convex optimization through divergent decomposition. So this is a brief outline of my talk. I will start first motivating why we should prove lower bound for first order optimization. And then I will explain how we prove lower bounds, and in particular, what is this technique using information theoretical tools. And finally, I'll show you what are these new lower bounds for a non-convex function that still have some kind of curvature. Okay, so first of all, what is the setting here? We are interested in minimizing a differentiable function from Rd to R. And we don't assume that the function is convex. The function might be non-convex. And we only have access to unbiased estimates of the gradient. Now, why we're interested in this problem? Because essentially, this is 90% of modern machine learning in these days. What people do every time they train deep neural networks, this is essentially what they're assuming. They have a non-convex function. They have access to unbiased estimate of the gradient, for example, through mini batches, and they're using some kind of first order algorithm. It might be SGD or it might be some variants of SGD, but they're all essentially SGD based. And depending on what are the characteristics of the function, typically we can prove upper bounds of the convergence rate of SGD or variants of it. Now, why we should instead look at lower bounds? So an upper bound basically tells you what is the best that your algorithm can do in the worst case. Instead, the lower bound tells you what is the best, what is achievable for any algorithm out there. It's not specific to a particular algorithm. So it's in a sense, a lower bound, it's not giving us any algorithm. It's not giving us any improvement. It will not make us winning any competition on machine learning benchmarks. And so why we should do it? Because sometimes there is a gap. There is a gap between the upper bound, the best known upper bound, and the best known lower bounds. And this typically means that one of the two is suboptimal. And sometimes we don't know which one is the suboptimal one. It might be that the lower bound is not powerful enough to capture the fact that it should be go up to the upper bound, or it might be the fact that the upper bound is actually suboptimal. So this means that we need a new algorithm. And so, for example, if you look at historically, this is exactly the way in which nestor of acceleration was developed. There was a gap between upper bound and lower bound. And in that case, the lower bound was optimal and the upper bound was suboptimal. So a new algorithm was developed. So we see, at least personally, I see these lower bounds as a way to gain knowledge rather than a way to construct basically new algorithms. Okay, so what is the classic way? The classic way is using these information theoretical tools. So what is the setting? A little bit more specifically, we are interested in minimizing this function from Rd to R, and I will always denote the minimum of the function with f star. We will have many functions. Each time f star will be the minimum of the particular functions that we are considering. And we will consider that, we will assume that the function is L smooth. And by that, I mean that the gradient is Lipschitz. We will not assume convexity, of course, and we will assume that we have stochastic gradients, so that I will denote in this way, nabla with a hat on top. And for these stochastic gradients, we will assume that they are unbiased. So the expectation given the particular x in which we are evaluating the stochastic gradient is equal to the true gradient that I want to evaluate. And we will also assume that we have some finite variance. These random variables minus this estimate, the norm squared condition on x is less than some sigma squared. Now, what we have to do, basically, you can use whatever algorithm you want. and you can request up to capital T stochastic gradients in any point that you like. And at the end of this entire procedure, you return some point x hat of capital T. Okay, it's important here that this is completely arbitrary. Do not think about SGD. I do not think about the fact that you have to return the last solution. You can do whatever you want, and then at the end you can return any of the solution that you generated. It doesn't matter. Okay. Okay. So the question is, what is the best rate that you can achieve on the suboptimality gap here that is defined as the expectation of f in the point that you returned minus the minimum? What is the best that you can achieve? Of course, like this, I mean, I don't assume anything else, in general, this problem is NP-hard, so we will assume a little bit more about these functions because, again, these are non-convex. Now, one might say, okay, this question is, sorry if this might be too elemental for the statisticians in the group, in the audience here, but again, I want to be sure that everybody understands. So if I just tell you what is the best that you can do in this sense, well, there is always one algorithm that will achieve the minimum even without requesting any gradient. And how this magic algorithm will do it? Well, it's very simple. The algorithm will just outputting a particular point that just happen to be the minimum of the function. So this means that for each function, I can always construct an algorithm that is perfect, right? So the question in this way sort of will post. I have to be a little bit more precise. So, and clearly, this is not a good algorithm because this is really just the only thing that this algorithm is doing is just outputting 1 point. For any function you give, it's always giving you 1 point, okay? So we have to be a little bit more precise on what we want. And one possibility instead is to say, okay, let me still consider this suboptimality gap, but let me take the supremum over all the possible function in a certain class, okay? And this basically will measure what is the worst case risk that we can have in a particular class. Now, we just consider the best algorithm that we can find. So we put an if in front of this expression, and we get the minimax risk for a particular class, given our set of hypotheses on how we access this function. Okay, and this is now the object that we want to study. So the way in which I look at these things, by the way, it's like a game, basically. The game is the following. You decide what is the optimization algorithm that you want to use, and I am your enemy. I look at your code, and once I look at your code, I decide what is the function that I want to give you. Okay, and so I'm basically constructing every time a function that it's very bad for your specific algorithm. Okay, this is important. There is no such a function that it's hard for everybody. It's a function that is specific for your algorithm. Okay, and given that we are considering all the possible algorithms in the world, this will tell us what is the best that we can do for all the functions in this class. Now, I want to also be very open about the fact that this concept is very general. This comes from statistics. It's not a concept from optimization. But I will specialize it just for optimization because this is what I care about. So how we do it? Basically, it's very natural to think that in this class of functions that we're considering, that again, I'm considering smooth functions plus some other assumptions that I will tell you in the following, what we do is that we isolate a few very hard functions, just a few of them, okay? And every time you give me an algorithm that I have to analyze and decide what is the hard function to give you, I just select among these few hard functions that I have, just one specifically for you, okay? So, moreover, remember that we say that we are accessing the gradients only through stochastic gradients. So this means that the problem of finding the minimizer, this just becomes a statistical estimation problem, okay? And so how statisticians do solve these kind of problems, there is a very common trick that is the idea that you take an estimation problem and you reduce it to a detection one. And in this way, we can use all the tools from information theory and statistics on the lower bounds, the probability that you can detect things. Okay, I will be more specific on this. Okay, so what's the recipe that we are going to follow? We basically define a family of distribution pi, and we also decide how many of this distribution we have. And now every time I have an algorithm, what we do is that we will select an index here, I, from this distribution uniformly at random. Once I have selected this index, I will give you a number of simples, capital T simples, from this specific distribution. And the job of the detector is to, given these simples and given the knowledge of the entire family of distribution, is to understand from which distribution the simples were generated. Okay, sounds good. By the way, feel free to stop me at any moment if you have a question, if something is not clear. And I will use a function psi that basically we'll call it a detection function that basically takes in input this set of simples, and in output it has to tell me which one of the function in my family of which one of the distribution in my family of distribution the simples are coming from. Okay, so this is the game. Okay, so now what is the connection between this game and the minimax risk in optimization? The trick is the following: we will always lower bound the minimax risk as some delta that essentially is the cost that you pay for the fact that the your optimization algorithm was not able to detect the area of the optimum, okay, multiplied by the probability of failure of the best detector. Okay, so you have here the infimum over all the detector functions that are out there of the probability that your detector algorithm is not able to detect the correct distribution. Okay, and this will be the way in which we'll prove all the lower bounds, and this is also the classic way in which we prove it. This is not by me. This is really the classic way in which people prove this lower bound. And the only thing that we have to now to understand is how to manipulate this probability here and how to quantify this delta here. Now, to give you a little bit of intuition, what is this delta basically? Remember that you have to choose the distributions. So if you choose a lot of distributions, delta is basically somehow measuring how separated are distributions one from the other. So if you have too many of them, delta will be small. On the other end, the probability of failure will increase because it's much more difficult to understand which of the distributions the symbols are coming from, given that I have a lot of them and they are close one to the other. Okay, and so in this case, this term goes down, but this term goes up. On the other end, if I choose just a small number of distributions, this means that the cases are very far apart one from the other. And I will show you that in this case, this term will increase. On the other end, the probability of failure will go down because now there are just few possibilities and they are very far apart from one to the other. So this is an easy job for the detector. Okay. Yes, yes. We will assume always that capital T is fixed. Yes. But for sure, yes, the moment that I get more simple, things become easier. Okay, so what are the tools now? Remember what are our job now? The job is to lower bound this term and to quantify this other term. So as I said, this is a generic technique. So this part is the only part that depends on the optimization part. So this delta will also depend on the particular function that we are trying to minimize, what's geometry and so on. Instead, this other part, this is a generic. This is a generic reduction. Every time you want to minimize, to reduce this estimation problem to detection, you will always have this term. And so now I'll show you how to lower bound this probability in a very generic way. Okay, this is actually very simple. We just have to use Pinsker inequality. Pinsker inequality says that if you have two probability measures, the total variation between these two probability measures, that is denoted in this way, is less than the square root of 1/2 of the KL divergence between these two distributions. Now, how do we use this small lemma? Remember, we want to lower bound this quantity, or I mean, we actually want to lower bound the 1 minus this quantity. So the probability that we fail, this is it's the same. So we can upper bound the probability that we are correct. So given that the environment is selecting the distribution at random uniformly, this by definition is just the average over the probability that you are correct every time the random variable is exactly equal to I. Okay, so for each one of them, there is a different probability distribution, and for each one of them, you can evaluate what is the probability that the detector was correct. Now, here is the moment that you use Pinsker inequality. Pinsker inequality tells you, let's go back here, that the supremum over A for any measurable A between P and Q in absolute value is bounded by this. So this means that the difference between this guy and any other Q is upper bounded by this additional term. Okay. And Q here is free. I can choose any fixed Q. This is always true. So now I also assume the fact that, I mean, I don't have to assume it. I know that these events are disjoint. Why they are disjoint? This is the probability that the detector is equal to I. And the detector is only giving me one possibility each time. So clearly all these events are disjoint. And so I can sum up all the probabilities here, and I get for sure something less than 1. And then I can use Jensen inequality to bring this sum inside. And so finally, I obtain this inequality. This is our key inequality. This says that the probability that the detector will make a mistake is at least 1 minus 1 over the number of probability functions in your family minus this scale divergence term. And this holds for any Q. You can choose the Q, you can choose the PI. You have a lot of freedom here. Okay, so we plug this term into the minimax risk, and you get that is delta multiplied by this thing. And now our job is to choose the probabilities here, to choose Q. And choosing the probabilities, by the way, will also implicitly choose delta, depending on what is the geometry of the functions that we are minimizing. Okay, sounds good. Any questions till now? Nope. Okay, so let's make an example. So maybe if it was not clear till now, if we make an example, it will become a little bit more clear. I want to show a lower bound for the optimization of 1D convex functions. Okay, this is basically a toy problem, but just to show you how we can show very easily this tool. So what is the protocol? You initialize the learner in some way. In each step, you choose an x of t, and you get a stochastic gradient in x of t. And then in the next step, you can do whatever you want. You basically add to your state the previous state, the current x, the stochastic gradient that you received. And then in the next iteration, based on the entire information that you have up to this moment, you decide the next point. Okay, so again, this is not SGD. This is much more generic than SGD. You can basically do update in any way you like. And then at the end, the final recommendation that you give is any arbitrary function of the entire state. So everything that happened allows you to select what is the actual point that you believe is close to the minimizer. Okay. Okay, so how do we construct now our lower bound? Remember, I told you we have to construct a family of difficult functions. So what is the family of difficult functions? 2 functions. We will have 2 functions. And we will assume them to be L-smooth. And we will assume that the functions are just defined on a bounded domain. So the optimization will be on a bounded domain. Everything is 1D because we are considering a 1D function. And what are these functions? The function is basically a quadratic. And the minimum is in a certain point zi. And it's a quadratic up to a certain distance from zi. And then it becomes linear, okay, from one side and the other. So it's a very simple one. It's quadratic, and then it goes up linear. And there are 2 functions. One is centered in 0. So one is the minimum is in 0. The other one is the minimum is in d divided by 2, where d is basically the radius of your domain. These are my two difficult functions that I want to construct. And here I also calculated the gradients of these functions. And the gradients are useful. This is the plot of the gradients because, okay, let me show you the next slide, and then we will go back to this one. Okay, so this is our stochastic gradients, our given by the true gradients plus noise. Let's also assume something on the noise. Let's make a very simple assumption. Let's assume that the noise is a Gaussian, zero mean, and the variance is exactly equal to sigma squared. Okay. So now we have to go back to that reduction that I showed you. We have to reduce this problem optimization to detection. Okay, this is the key point here. How do we do that? Let me define the event EI, the event in which the point that you returned is far away from the actual minimizer. Okay, and there are two functions here. So I can be just function 1 or 2. And so there are two possible points, Z1 or Z2. Okay, so this event is saying, unfortunately, you return the point that it's not close to the optimum. Okay. Now, the expectation that the suboptimality gap, this is a suboptimality gap because the minimum is in 0. So this is exactly suboptimality gap. The expectation, how I can lower bound the expectation of the suboptimality gap for one of the two functions. This holds for both functions. This is greater than the probability that this event is false multiplied by the infimum of the function in this region, plus the probability that the event is correct, multiplied by the infimum outside of this function, of the infimum of the function outside of this region. Okay, so what's the idea here? Basically, you're saying, how far are you from the optimum? Where there are two cases. With a certain probability, you were actually far from the optimum. Okay, so with a certain probability, you are far from the optimum. Now, if you are far from the optimum, what is the best that can happen? The best that can happen is that you get the infimum of the function outside of this radius. Okay. On the other end, what can happen is that you were actually close to the optimum. So with a certain probability, you are close to the optimum. And in that case, what is the best that can happen? The suboptimality gap is the best of the suboptimality gaps inside that region close to the optimum. Seems good. Is it clear? So next, you say this is positive. Away. And let me just keep these two terms, this probability and this other term. This other term can be calculated exactly. I can calculate exactly what is this infimum here. And this infimum turns out to be this value, L delta D divided by 8. Well, delta was basically the moment in which the function becomes from quadratic to linear. So it was a parameter of the function. Okay. So I want to stress this step here because this is important. If you notice here, on this side, this depends on the algorithm, right? This is the output of the algorithm. But on this side, any dependence on the algorithm disappeared. Nothing depends on the algorithm anymore here. Because this is, I mean, it depends on this part, but it doesn't depend on this part anymore. And this is exactly the way in which we prove something that is uniform for all the algorithms, exactly in this. Okay, so now that we have this equality, we can prove our minimax rate. So the minimax rate is the infimum over all the possible algorithm of the supremum over all the possible function in our class of the expectation of the suboptimality gap. The next step that we say, instead of considering all the possible functions in this family, let me just consider two functions. This is always the lower bound, right? Because these two functions are in the class, so this is always the lower bound. And let me do another lower bound. This is the max between two numbers. The max, it's always bigger than the average. So now I have the average of the suboptimality for one function plus the average of the suboptimality plus the value of the suboptimality of the other function divided by 2. And now I can use this lower bound here. The suboptimality of these is greater than the probability that you are far multiplied by this constant. And so now I get this constant, the probability that you are far in one case, plus probability that you are far in the other case. These are the two functions. Okay, now we need the lower bound of the probabilities. Now we can use Pinsker inequality. And Pinsker inequality tells you that this thing is lower bounded by 1/2 minus the KL divergence between P1 and P2. Okay, we're basically done at this point. The only thing that we have to calculate is this KL divergence. But this is easy because we know everything about these things. These are just Gaussian random variables. And so we have this term. We can just calculate, we can just upper bound this KL divergence between these two, keeping in mind that this is basically the product distribution of all these Gaussian variables that you observed, right? Because each time you query a gradient, this is a Gaussian variable, and you query another. And notice that there is some dependency here because basically you are selecting the next point based on the past points, but this still works. You can still upper bound these things with t times the KL divergence between two random variables. And you just, and these random variables basically are the difference between the gradient in one point on one function and the difference between the gradient of on the same point of the other function. Now you just take the supremum between these two, and this is exactly why this plot of the gradients here is useful. We constructed the two functions in such a way that the difference, this is the plot of the gradients for one function and for the other function. The difference between these two is bounded. So we know exactly how to control the difference between the gradients of these two functions. And so we have that the difference here will be proportional to t, will be proportional to delta squared, that again was the parameter of the functions. And so you have this term. Finally, this is your final lower bound. Remember that delta here was free because it was the moment in which the function switches from quadratic to linear. It's a completely free parameter. We can choose any delta that we like. What is the delta that we like? It's the one that maximizes the lower bound. If we maximize over delta, we finally get this expression that is exactly the optimal lower bound for optimization of convex 1D function. Okay, makes sense? I hope it was not too technical. But if you ever want to prove a lower bound in your life, these are basically the steps that you want to follow. Okay, so at this point now, as I promised, let me see how much time I took. How much time do I still have? Okay, so I can do it. So at this point now I can tell you what we have done. This is what I showed you till now. This is known stuff. This is sort of stuff that you read in the books. And for example, if I want to some suggestion, there is John Ducci as a massive book on machine learning in general, but there's a number of chapters on estimations and how to prove lower bounds. So this, you will find all these kind of things there in a more complex way, if I might add, but these are all known tools. Now, let me show you instead the new stuff that we have done. Okay, so now, remember, we want to attack the problem of proving lower bounds for non-convex functions. So in general, you cannot even find, we know from the beginning that it's impossible to find the global minimum in general of a non-convex function, okay? So if somebody asks you for a lower bound, you can just say, you know, this is MPR, that's it, there is nothing to do. However, there are a lot of non-convex functions that are benign in the sense that even if they are non-convex, we can still optimize them. And we can optimize them with extremely simple algorithms like SGD. We don't have to do anything too fancy. So for example, if I give you this function x squared plus x sinus of x, this is non-convex. But if you run SGD on this thing and you access gradients plus noise, I can assure you, you will converge to the global optimum. And I'll show you in a moment even the plot of this function. So what are these class of functions that are benign, and what are and why people are interested in them? We consider three classes of functions and intersections between them. First of all, let me denote by X star the set of minimizers of F. That we don't assume that the minimizer is unique, so it might be even infinite number of them. The first notion is called Quasar-Convex. And basically, if you put tau equal to 1, this is just convexity. So this is f of x minus f star is less than the gradient between of f in x and x minus, and this guy is the projection of f of x into the set of the minimizers. Okay, if there is a global minimum, this is just x star. But if there is no global minimum, this is the actual precise definition. Okay, so if you put tau is equal to 1, this is just convexity. But if tau is not equal to 1, then you have functions that are non-convex, but essentially, you know, they have this nice property that they look almost convex in a certain sense. Then there are two other family of functions that instead they can be looked as weaker version of strong convexity. Strong convexity, I don't know if you're aware, strong convexity is basically says the function is lower bounded by quadratic. Every time you have strong convexity, you can have fast rate if you're in the stochastic setting, and you can have linear rate if you're in the deterministic setting. So there are functions that are very easy to optimize. There are weaker versions in the non-convex world. So one is called quadratic growth. So f of x minus f of x star is greater than x minus, let's say, x star here for simplicity, up multiplied by a certain factor mu that will be the parameter of the quadratic growth. And this says basically that the function f is growing away from the minimizer as a quadratic in the difference between x and x star. And there are non-convex functions that satisfy this condition. Another one is the restricted secant inequality that says instead that the gradient of f of x comma x minus x star is greater than mu multiplied the distance square between x and x star square, x and x star. And now, if you have strong convexity, you will have that this will immediately imply the restricted secant inequality, and the restricted secant inequality also implied the quadratic growth. So you can see that hierarchy of way of how to weaken these conditions. Now, why we consider these things? Well, because I work in machine learning, and in machine learning, these conditions were actually proven to be true in certain neural networks. So in particular, in this paper, they showed that these conditions are true at least at the initialization of neural network. You know that they are initialized with random noise, and random noise satisfies certain conditions. So at initialization, you are in a very nice place, let's say. So at least at initialization, these conditions are true. And in this other paper, instead, they proved that Quasar-Convexity appears the moment that you want to minimize linear recurrent neural networks. And so this means that basically, you know, this problem, even if they are non-convex, they might be actually easy to optimize. And this might be the reason why, you know, people actually use SGD and you do optimize them. It is actually true that most of the time you will actually converge to the global optimum. Okay, so this is an example of a function that is Quasar-Convex and satisfy the restricted secant inequality. And this is exactly the function that I showed you at the beginning, x squared plus x sine of x. You get this kind of function that is non-convex. But if you run gradient descent, you will converge to the optimum. Okay, so let me, without further ado, let me tell you what are the bounds that we proved. So we consider three different scenarios. We consider the case in which the function is quasar-convex and smooth. And we need this technical assumption that the dimension of the space is large enough compared to the constant of the quasar-convexity. And also T is large enough compared to the smoothness constant. And then for any optimization algorithm, I can always construct a function that is L smooth, tau quasar-convex, such that the suboptimality gap will be at least of the order of sigma, where this is the variance of the noise, tau divided by square root of log 2 over tau, square root of t. So let me point out the surprising things. The first surprising thing is actually you do converge in this case. I mean, and by the way, we also proved upper bounds for these classes of functions that I'll show you, and the upper bounds match. So we know that this lower bound is optimal. So the first surprising thing is that SGD will converge on this class of function. The second is that SGD will actually converge at the optimal rate if you use a learning rate that is done in a certain way. And the other thing that it's these two factors in black that are interesting, you pay a price that depends on the Quasar-Convexity, this Quasar-Convexity tau. And this is the new factor. It's very easy to show bounds that do not contain this factor. And basically, every time you do that, you're basically assuming convexity. Because if tau is equal to 1, you're assuming convexity. But it's difficult. The difficult part was to characterize this dependency on tau. And again, this dependency is optimal because we can prove a matching upper bound even in tau. The other case that we considered are quasar-convex, quadratic growth, and smooth. So here, what you would expect is a rate similar to strong convexity, because quadratic growth is basically a weaker notion of strong convexity. And we get here that in fact, you get a rate that is 1 over t. So the rate that you would expect for the strongly convex case in the stochastic case. But again, you pay a factor that is tau square log of 1 over tau that depends on this quasar-convexity thing. And this was the difficult part to characterize. And again, this dependency. The last case is the case in which the function is as restricted secant inequality and smoothness. Again, you would expect here some fast rate because this is a weaker notion of strong convexity. And in fact, you get the fast rate 1 over t. But what is the surprising factor? The surprising factor is this kappa factor here that is basically, if you want, some notion of condition number. And this kind of factor is not present in the convex world. If you just assume strong convexity, this factor is not there. And so there is a gap between the strong convexity case and this restricted secant inequality that seems due to the fact just that convexity is giving you basically a huge advantage because kappa can be arbitrarily large. The condition number here can be arbitrarily large. Okay, so and as I said, these are all optimal because we also showed matching upper bound, so everything is optimal. I don't know how much time I have, but let me show you now what is the proof idea. Given what I explained all you before, now this should be easy. So what are the steps? We have to construct a family of differential functions, and we also have to refine the information theoretic lower bounds that we had before. That KL divergence term is not strong enough. So this was our contribution, and these two things are coupled together. We can construct harder family of functions exactly because we have a more detailed control on the KL divergence. Okay, so this is what the starting point. This was, again, what we got from Pinsker inequality. This was the generic tool that you use every time you want to prove your lower bound. And this is the term that you have control, this KL divergence term. Now, what we did, if you look at the non-convex world, the non-convex world gives you a lot more freedom in the way in which you design functions, because the first derivative can be non-monotonic. This is not true in the convex world, but now we can design these things. And so what we can do is that we can design functions that are almost flat in an area that is outside of the area of the minimum. So you will have the minimum somewhere, then a flat area, and then some part that grows fast because we need this quadratic growth part. Okay, and this flat area is the part that makes this KL divergence small. And if the KL divergence is small, the lower bound is better. And so in the convex world, what we did was just t times and the supremum of the difference of derivatives. But now, given that this would not work if I want to use this fact that there is a flat area, because the supremum here will ruin everything. The moment that you take the supremum, you have to consider all the possible area of your space. And so this is the key idea, this divergence composition. The idea is that you take this KL divergence and you upper bound with two different cases. When you are in a certain area, multiplied by the number of times that you request a point in that area, plus the gradient when you are outside of this certain area, multiplied by the number of times that you're outside of this certain area. Okay, it's a very simple idea. I mean, we're just saying, let's divide the KL in these two different cases. And by the way, this idea comes from online learning. This is a tool that was developed from online learning people to prove lower bounds, but for bandits, multi-arm bandits. And this is the first time that somebody used it to do lower bounds for optimization. Okay, so this is the basic idea. So basically, we have now these two different terms. And by the way, here we have the total number of times minus the number of times that you're in a certain area. We just upper bound it with just number of times, the total number of queries. So we have these two terms. And now the other small ingredients is to say, let me construct these different areas in a way that they are disjointed. So every time you are in one area, you are also not in another area. Okay, so they are all disjointed. So this means that the sum of times of all these ni, that remember, ni is the number of times that you are in the area Si. This is less than the total number of rounds. And so when you sum now these scale divergences and you take the average of all the possible functions that you have, now you will have these two terms. One that is when you are in a certain area, and this is divided by the number of functions that you constructed. And then you have these other terms that when you're outside of a certain area. And this is the critical ingredient that we need in order to construct our more powerful lower bound. And now you are free to choose these areas. You're free to choose your functions. You're free to choose the distributions so that the KL divergence is as small as possible, but at the same time, you want the optimization, the error that you commit when you are far from the optimum, as large as possible. Remember, there were two terms, delta and probability of detection. And so what are the functions that we end up constructing? They basically look like this. We decide what is the optimum. This is in 1D, but you can clearly do this in any number of dimensions. So you decide where is the optimum. You center something like a quadratic around the optimum. Then you have an area that is outside here, that is the flat area. It's exactly the part that buys you a small KL. And then you have an area that where the functions grows very fast because you need this quadratic growth. We need everything to be lower bounded somehow by something that looks like a quadratic. And so this is the plot of the derivatives. And you can see that in this area, the derivative is constant. It's constant and it's very close to zero. And this is the area of the optimum. And you see that here, clearly the derivative is non-monotonic. And you can do this thing because the function is non-convex. And then you have to very carefully decide all these parameters here so that the function is exactly L smooth, as quadratic growth, as exactly the Quasar-Convexity. So these are pages and pages of incredibly boring calculations on these parameters, on how they all fit together. Okay, that's it. I'm basically done. So what we proved are these optimal lower bounds for smooth quasar-convex, smooth quasar-convex plus quadratic growth, and smooth restricted secant inequalities. And to do that, we use this new method. We propose this new method to prove lower bounds that is tailored to non-convex functions. Unfortunately, we cannot prove a lower bounds for what are called PL functions that are non-convex functions that satisfy this property, and they're particularly fashionable, let me say this way, in machine learning in these days. We actually started with this problem, we could not prove it. And this paper, by the way, will be presented at COLT. And the main author I want to stress of this thing is my postdoc Al-Mehdi, that I don't know if it is in the room or not, but he was really the main mind behind all this. Okay, thank you. Yes. Right.
Sorry. So why was it hard to prove it for PL condition?
Because if you see, we basically had to introduce this. We started from Polyak. This is what for PL function. This is exactly what we wanted to prove. And because, by the way, when you minimize a PL function, you get exactly that kappa factor. And we wanted to show that that kappa factor is optimal. And as far as I know, it's still unknown. And the key difficulty in the proof is that the moment that there are certain things that do not work in the right way, and even in this case, by the way, we had to assume these additional Quasar-Convex things that makes things easier. This condition basically, if you want, this condition basically says the gradient it's true that the function is non-convex, but the direction of the gradient is still in the right, because this is positive here, right? Because this is f of x, this is f of x star, so this is a positive quantity, this is non-negative, and so this inner product here, it's always non-negative, and so the gradient, it's always pointing you basically in the right way. With PL, there are a number of technical problems that didn't allow us to carry it. However, we can show that we don't know if the proof technique that we developed with this divergence composition, it's actually the right one or not, but we can show that the original one, the one that does not use it, will fail for sure. Okay, so at least that.
That's good. Another question is, how hard would it be to reproduce this without the assumption of finite second moments or bounded domain?
Oh, the bounded domain, we actually don't need it. We need bounded domain only in this case. Only in this one we need bounded domain. Here we don't need bounded domains, and here we don't need bounded domains. Now, what you asked about second moment?
Maybe having something like a
I don't
constant,
think,
but something that is growing quadratically or growing exponentially.
So sorry, you want to weaken the noise assumption?
Yes,
you want something like an affine noise assumption?
Yes, yes.
I don't think it would be crazy. I don't want to overpromise, but it might be doable. Might be doable. What it might be easier instead, it would be probably to say, instead of assuming that the second moment is bounded, you assume some kind of heavy tail noise, and then you try to bound the KL divergence in that case. I think that is doable. That might be easier than the affine noise.
Can I have one more question? So now that for this specific class of problems, you showed that the optimal lower bound has the influence of the condition number. So do you think this could motivate using preconditioners to reduce the effect of this condition number?
Oh, this is a very good question. This is an extremely good question. We should work on this. Yeah. Oh, okay. So yeah, this is a very good idea. Yes, I am not aware of anything in this direction. Yes, definitely. And by the way, in these days, there is a lot of work on algorithms that are not exactly second order, but I don't know if you're aware of this shampoo, muon, yes. So yeah.
Kind of based on natural.
I see.
Based on natural gradient descent, right? I guess shampoo. Yes.
I see.
Yep. Thank you very much.
Related question. So, what is your experience with or at least what is your advice for stochastic optimization that is in hypothesis of the function, right? Which are the algorithms that you would recommend for stochastic?
For convex.
Convex, yeah.
Stochastic. I mean, stochastic convex.
The bundles for the deterministic, right? So, what is your experience with the bundles, for example, for stochastic? Would you still recommend them?
I mean, stochastic and convex, I would recommend some kind of variance reduction. It always helps.
Yes, for sure. But in terms of bundles are used to where the function is going. And I'm talking about convex, possibly non-differentiable, right?
Possibly non-differentiable. I see.
Sorry for this ambush, but this is an interesting program.
But what do we know on the function? The function has some kind of strong convexity, or
yeah, but you have subgradients in principle, right?
subgradients are fine. But okay, so if you don't want to reduce the variance,
no, you can.
You can reduce the variance, but it's not mandatory. Let's say I do have an algorithm that adapts to the strong convexity parameter. Because in the
It works with subgradients.
It works with subgradients. It works in the stochastic case.
Multi-D, no problem. Multivariate.
Yeah. Even Banach spaces if you really want.
Okay, cool.
Because typically you get a fast rate if you know the strong convexity, but if you do not know strong convexity, this thing can be arbitrarily bad. And how do you know strong convexity? You basically have to try all the possibilities because nobody tells you the strong convexity typically. And as far as I know, I have the only algorithm that for the stochastic, strongly convex, non-smooth case that adapts to the strong convexity automatically.
Because our problem can somewhat do a relaxation, so that's why we get for sure.
I see.
Convexity that concavity in this case, but it doesn't matter.
I see. Okay. I see. We can talk.
Yeah, definitely. I'm pointing the right person in the audience to
Okay.
be aware of this connection, so she doesn't miss the point. Okay, so we should thank once again our last speaker. Well, this is a very interesting moment, right? We're concluding the workshop. I would like to thank all of you for the contributions in the nice interactions we had, all the speakers that gave fantastic talks. I'm very glad also that this material will be, at least partially, for those that are visible in YouTube, right, where we have our channel. And of course, we already put abstracts and all the related information. I love the trip to Alula also. Had a great time for those that came with me. And of course, we will try to read this if possible. Finally, I'd like to thank also all the team. I mean, Aku and Carlon, who very stoically were here producing these recordings, right, of all the talks. I mean, very silently and helping the speakers to get ready. Thank you, guys. I mean, we love you, right? And you get something. I don't have it with me, but I will give you something to recognize it that I did in the previous workshops too. I want to thank also Saman, who is not here, but she put an enormous work throughout the year to put all the pieces together of logistics that are needed to run this thing for such a time. And Roxana, of course, who volunteered and put the logistics as well together with Saman, right? That she did an enormous work in that respect. So thank you so much. I'm very, very happy. Thank you. Actually, who has something for Kayan tomorrow?